All right, welcome to Right Triangle Trigonometry for College Mathematics. We have a total of 6 goals for this section. We need to make sure you can identify the trig ratios, that you can use your calculator to find both the ratio and the angle using inverse trig ratios. We want to make sure you can find unknown parts of a triangle using trigonometry, which includes fully solving that right triangle. Along with that, we're going to show you some applications that you can use trigonometry to solve for both a missing side and a missing angle. Let's get started by identifying the trig ratios. And those 3 that we're going to be working with are the sine, the cosine, and the tangent. To begin, we need to start with a right triangle, which we're going to call ABC. Naming or calling out the right angle at C, that tells us that the hypotenuse is directly across from that right angle. That entire side, AB or BA, would be the hypotenuse, which we will label with an H. The hypotenuse is labeled first because it is always identified as the side opposite the right angle. It does not change or alter. It has to be opposite the right angle in the triangle. The other 2 sides are relative to the angle. If we're looking at angle A, then the side opposite angle A is BC. This would be opposite the angle, and we would indicate that with a capital letter O. The side adjacent to angle A, I've highlighted in green. That adjacent side would be indicated with a capital letter A. The 3 trig functions, the sine of angle A, written S-I-N or sin, is actually pronounced sine. The angle that we're referencing is next. It's the sine of angle A. The sine of angle A is the ratio of the side opposite that angle to the hypotenuse of the right triangle. The second ratio that we're going to be talking about is that of the cosine. The cosine of angle A, abbreviated COS and then angle A, is the ratio of the side adjacent to angle A when compared to the length of the hypotenuse for the triangle. The third and last of the trig functions that we'll be studying is the tangent of angle A, abbreviated TAN, and given the reference angle A, the tangent is the ratio of the side opposite angle A when compared to the side adjacent to angle A. These 3 trig functions are often abbreviated using the acronym SO, as in sine is opposite over hypotenuse, CA, as in cosine is adjacent over hypotenuse, and TOA, for the tangent is the opposite side over the adjacent. You will often hear SOHCAHTOA mentioned numerous times in relationship to trigonometry. Let's try a few problems. Keeping the SOHCAHTOA down the far left-hand side, we have 2 right triangles. Taking a look at the very first right triangle at the top, you can identify the hypotenuse H as 13. That is the side opposite the right angle, so it is the hypotenuse. The side opposite angle A would be the 5, and the side adjacent to angle A would be the 12. Since both the opposite and the adjacent were done in reference to angle A, we'll start there. So for angle A, the sine of angle A is the ratio of the length of the opposite side to the hypotenuse. Since 5 is opposite and 13 is the hypotenuse, the sine for angle A is 5 over 13. The cosine for angle A is the side adjacent when compared to the hypotenuse. In this case, adjacent to angle A is the side 12, side of length 12. The hypotenuse is the side of length 13. So this would be 12 over 13. The tangent for angle A is the side opposite over the adjacent. That's where we get TOA. T for tangent, O for opposite, and A for adjacent. The tangent of angle A would be the length of 5 when compared to the length of 12, or 5 over 12. In this case, all of these are written as fractions, but they could easily be converted to decimals. If we look at angle B, now, if we're referencing angle B, then the side that is 5 is actually going to be the adjacent side to angle B, and the opposite side would be the side that is 12. So the relationship sine, cosine, and tangent is dependent upon the positioning of the angle. Because we're now standing at angle B and looking out, the sine would still be the side opposite when compared to the hypotenuse, but the side opposite is now the side that is 12 units of length, and the hypotenuse is going to remain the same no matter what in a right triangle, and that's going to be 13. So the sine becomes 12 over 13. The cosine is still the adjacent side compared to the hypotenuse, but now we're standing at B. So the side adjacent to angle B is 5 units in length. The hypotenuse is still 13. So this is 5/13. The tangent is still the side opposite when compared to the side adjacent. Because we are now looking at it from angle B, the side that is opposite is 12, the side that is adjacent is 5, and the tangent for angle B is 12 over 5. Let's take a look at the second right triangle. In the second right triangle, we see we have a hypotenuse of 25. If we're at angle A, then 7 is the side opposite, and 24 is the side adjacent. So the sine for angle A would be 7 over 24. The cosine is the adjacent side when compared to the hypotenuse. So for angle A, the cosine would be 24 over 25. Similarly, for angle A, the tangent is the side opposite angle A when compared to the side adjacent to angle A. This would be 7 over 24. If we switch to angle B, so I'm going to switch the angle I'm referencing, that is going to switch the opposite and the adjacent sides. So for angle B, the side opposite is now 24, making the sine the opposite over the hypotenuse. That part remained the same, but that's now going to be 24 over 25. For the cosine of angle B, we have the side adjacent to angle B when compared to the hypotenuse, or 7 over 25. For the tangent of angle B, it is still the opposite over the adjacent, but because we're at angle B, the view has changed, and the side opposite is 24, and the side adjacent is 7. Moving on to 3 additional triangles. Here we have 3 right triangles. The first one would be of sides 3, 4, and 5, the second of 6, 8, and 10, and the third of 9, 12, and 15. These 3 triangles are similar in that they are simply the 3, 4, 5 triangle doubled and then tripled to get the 6, 8, 10, and the 9, 12, 15. So when we take a look at the sine for the smallest triangle, angle at alpha, we will see that the sine is the opposite over the hypotenuse, or 4 over 5. The cosine is the side adjacent to alpha over the hypotenuse, or 3 over 5. And the tangent for angle alpha is the opposite over the adjacent, or 4 over 3. What's interesting about this is that when we doubled each one of those sides, angle beta looks considerably larger, but if we take the side opposite and compare it to the hypotenuse, we get 8 over 10, which is still going to simplify to be 4 over 5. The cosine of angle beta would be the side adjacent, or 6, when compared to the hypotenuse, but 6 over 10 reduces to be 3 over 5. If we take a look at the tangent will be the side opposite when compared to the side adjacent, or 8 over 6, which still reduces to be 4 over 3. Tripling it does not matter. Sine of epsilon, that's the little e, epsilon, would still be the opposite over the hypotenuse, or 12 over 15. This would be 4/5. If I look at the cosine of epsilon, that's going to be the side adjacent when compared to the hypotenuse, or 3 over 15. 3 over 5, 9 over 15, which reduces to 3 over 5. The tangent of epsilon would be the side opposite when compared to the adjacent side, or 12 over 9. And guess what? That also reduces to 4 over 3. These became so common that that there was a chart for it. Now, this chart or table can be used to find the sine, cosine, and tangent of any integer angle measure. Do you know an angle is 25 degrees? If so, you can come down here to 25 degrees and you can follow that across. Calculate, and without calculation, you have a table that gives you the sine, the cosine, and the tangent for 25 degrees. Because that sine, cosine, and tangent, that ratio, needs to be consistent no matter the size of your triangle, no matter how large or small it is. That takes us into the next step, which is trig ratios and the calculator. So, aside from that table, what was eventually done was that we programmed your calculators to be able to find the trig ratios. So we're going to go over using your calculator in this section. Here we're going to start. I've got the first example with a right triangle that has an angle measurement of 60 degrees, a hypotenuse of 10, and the other two sides being 5 and 8.660. Notice the side is done to a minimum of 3 decimal places. 4 digits, 3 decimal places. Let's take a look at that. If I'm looking at the sine of 60 degrees, the sine for 60 degrees, at 60 degrees, the sine has to equal the opposite when compared to the hypotenuse. That's the SOHCAHTOA. Sine is the opposite side compared to the hypotenuse, or 8.660 divided by the hypotenuse of 10. The cosine of 60 degrees has to equal the adjacent side to the 60 when compared to the hypotenuse, or 5 over 10. The tangent of 60 degrees has to be the side opposite 60 degrees when compared to the adjacent side, or 8.66 over 5. Dividing these out, we get the decimals. 8.660 over 10 is 0.8660. 5 over 10, 1/2 or 0.5, keeping all 4 decimal places, 0.5000. The tangent of 60 degrees is the 8.660 divided by 5. Converting that to a decimal, I get 1.7321. All of these represent the sine, cosine, and tangent for 60 degrees, which we would have picked up from the table. If we look at the second example, the sine of 47 degrees. The sine of 47 degrees would be the side opposite the 47 when compared to the hypotenuse, or 4.3881 divided by the hypotenuse of 6. The cosine of 47 degrees would be the side adjacent, or 4.0920, divided by the hypotenuse, which is 6. The tangent would be the opposite over the adjacent, or 4.3881 over 4.0920. Each one of these can be calculated out, giving us 0.7314 for the sine of 47, 0.6820 for the cosine of 47, and 1.0724 for the tangent of 47. It's worth referencing that each one of these can be found using the table. If I go to 60 degrees, 60 degrees is where? 60 degrees, I got it. And I look at the sine of 60 degrees, I have 8.660. Notice the tangent of the cosine of 60 degrees is 0.50 and the tangent is 1.7321. Similarly, if I were to look for 47, and if I were to look at the sine, I'd have 0.7314. The cosine is 0.6820, and then the tangent is 1.0724. It certainly is nice to have these in the table as well. All right, so now let's use these and see what we can do. I'm going to start with the sine of 11 degrees. In order to find the sine of 11 degrees in the table, I'm going to look down the sine column and find 11 degrees. When I do that, the cross section of the sine of angle A, or 11 in this case, and the 11 degrees, I have 0.1908. If I were to have to calculate the the cosine of 53 degrees, I'm going to look at the cosine, but I'm going to look in the second set of 3 because it's 53 degrees. And I'm going to look for the cosine of an angle, specifically 53. I'm going to find that intersection, and that is the cosine of 53 degrees. It's 0.6018. The tangent of 82 degrees. 82 degrees is going to be in the second part, but I'm going to look down tangent, and I'm going to find 82 degrees, and that intersection will tell me 7.1154. So 7.1154 is the tangent of 82 degrees. All right, clearing out what we've got here. This brings us to the idea that there is a way, if the ratio is known, to back find the angle, called an inverse function. It's essentially a reverse lookup. The notations for finding those angles are as follows. Sine with a -1 on it is known as the inverse sine, or the reversing of the sine function. Cosine with a -1 function, -1 exponent, is known as the inverse of cosine, and it takes the ratio and works it backwards to find the angle. Similarly, tangent inverse is the inverse of the tangent function. It means you were given the ratio and you're looking up the angle. So let's try. If we have sine inverse, that's sine -1 is pronounced sine inverse, of 0.9816. I'm going to look down the sine column and I'm going to find 0.9816. Once I get there, I'm going to look over to the side to see what angle measurement is there. In this case, it's 79 degrees. So the sine inverse of 0.9816 is 79 degrees. To do a cosine inverse. For cosine inverse, I'm looking at 0.4067. So I'm going to go down the cosine and I'm going to find 0.4067. When I do, I see that that hits at 66 degrees. So the inverse cosine of 0.4067 is 66 degrees. The tangent inverse of 0.2679 means I'm going to look up 0.2679 under tangent. I'm going to find 0.2679 under tangent. And when I go across to find the angle measurement associated with that, I have 15 degrees. So the inverse tangent of 0.2679, wait, what? Looks like I copied that wrong. Hold on. That should be 15 degrees. Let me get this, 15 degrees. I must have looked something else up. Oh, I think I copied up from above. So that should be 15 degrees. All right. Now, you don't want to have to look up the table all the time. You would much rather use your calculator. Given the standard calculator recommended for this course, your 3 trig functions, sine, cosine, and tangent, are highlighted there in yellow. If you need an inverse function, you need the small little green lighting up above it. So you would hit the second button and then whatever function you need. So let's take a look at using the function when you know the angle measure. So if you know the angle measure is 21 degrees, then the sine of 21 degrees just means you hit the sine button and then 21. The sine of 21 degrees should be 0.3584. Similarly for cosine, the cosine of 18 degrees just means you're clicking cosine and then 18 to get 0.9511. The tangent of 60 degrees, which we've done already, should be tangent and then 60. Hit enter, and you should get 1.7321. Cosine of 44 degrees. You try. It should be 0.7193. Sine of 73 degrees. We should get 0.9563. Notice you're using the straight up function when you already know the angle measure. If we need to find the angle measure, then you're using an inverse function. So if I have a ratio of 0.8874, the inverse sine of 0.8874 gives me 65.4 degrees. In order to use this on my calculator, I'm going to hit second first and then the sine. So we're going to click second and then sine and then type in the 0.8874. Then when you hit enter, you should get 65.4. If we need the tangent inverse means we'll hit second tangent and then whatever ratio or side length we have, 2.6154. Make sure to close your parentheses and hit enter, and we should get 69.1 degrees. For the cosine inverse, we're going to hit second and then cosine, 0.2215 in this case, to get an angle measurement of 72.2 degrees. I then have a practice for the sine inverse of 0.4449. That would be second, then sine, then 0.4449. Be sure to close your parentheses and hit enter. That should get you 26.7. Lastly, we have another tangent inverse. Again, we're looking for the angle when we use the inverse function. So we're going to hit second tangent, then 0.6734, closing the parentheses, and then hitting equals. We should get 34 degrees even. This brings us to part 3, or goal number 3. For goal 3, we're going to work with these inverse trig functions and show you how it works inside an actual model. So getting out a calculator, if you have one handy, or if you're pulling it from your phone or a computer, you can still use those. So make sure you have one of those ready. It's best if you can come along with as we do this. All right. In this, we're using our calculator to solve for angles, and we want to round to the nearest tenth of a degree. Again, on a standard calculator required for this course, we're using the sine, cosine, and tangent buttons that are highlighted in yellow. The trig functions, the inverse functions are what find your angle measurements, and you need to hit second first, and then whatever function you have. So let's try this first one. We have the sine of beta is 0.5642. In this, the beta is not known to us. That's the angle measurement. It is not known. So what I need to do is the opposite of sine on the 0.5642. The way that we write this is that our beta is going to be the opposite of sine, or sine inverse, on 0.5642. So I'm going to type into the calculator second sine and then 0.5642. And when we hit enter, we should get that beta is equal to 34.3 degrees. A second example, we have a different trig ratio. This time I'm using the tangent, and I've done just angle A. Notice that we've left the ratio of the sides, pi over 4. It looks way more confusing, but the process is the same. I have to do the opposite of tangent on both sides. That's going to leave me with angle A is the tangent inverse of pi over 4. Don't let this mess you up too much. You can use the pi button on your calculator or whatever calculator you're using, and then divide it by 4. Essentially typing into your calculator exactly what is written there. So we'll do second tangent, then we'll hit the pi button on our calculator. On this calculator, the pi button is right, I think it's the fourth one down. There's your pi button right there. There we go, pi button right here. So we'll use that for pi button, and then you can hit divided by right here, and then 4, and then make sure to close your parentheses. When you do that, you should be able to hit enter, and you will get angle A is 38.1 degrees. Trying the next one. If we try the next one, what we have is, let me erase these guys. There we go. Cosine of phi is the square root of 2 over 8. Since it's the cosine of phi, I need to reverse that cosine. So phi would be the cosine inverse of the square root of 2 over 8. And all I'm going to do on my calculator is I'm going to hit second. I'm going to hit second. So this guy. Then I'm going to go for cosine. That's this guy. It should open up a parentheses. Then I want square root, which is again second, and then x squared, 2 divide by 8. I might need a parentheses in there. Let's see. It would be second. Let me go through that one again. Just a second. I'm going to erase that. I think on this calculator and maybe on some others, and we want second, yep, cosine, yep. Then that should open up, yep, parentheses. Then we're going to do second to get us back to square root. That's going to open up a parentheses. We're going to say 2. I think we're going to need to hit the parentheses again to close that first one. And then we can hit divide by and 8. And then we can hit parentheses again to close it. Once you've got all that in, then we can hit enter. And we should get that, what did I say that was? Phi. That phi is 79.8 degrees. Okay. Should we try a couple more here? All right. I've got 3 more. If you feel confident, go ahead, but I'm going to go ahead and go through these. For cosine of angle B, I've got 0.0358. That means that angle B would be the cosine inverse of 0.0358. That's second cosine, and then 0.0358, which would give us an angle that is 87.9 degrees. The next one that I have here is sine of alpha is 4 over 5. We know 4 over 5 is 0.8. If you would rather use 0.8, you're welcome to do so. But you can also just do sine inverse and then 4 over 5 and type that in as you see it. When you do and you hit enter, you should get 51.3 degrees. And for a last and final example in this section, we've got the tangent of angle A is 7.4423. So I need to undo the tangent using the inverse tangent function. So second tangent, 7.4423, which would then give us angle A is 82.3 degrees. All right. Here we have an application where we do know the side lengths. I have the hypotenuse as length 18. I have the adjacent and opposite sides as 15 and 9.550. So if we're going to look at the sine of angle A, for angle A, we have the side opposite compared to the hypotenuse. So if we do the opposite over the hypotenuse, we will get 9.950 over 18. So sine A is 0.5528. If I'm looking for angle A, that means I need to take the inverse of that. So angle A is the sine inverse of 0.5528 or 33.6 degrees. If I didn't want to do sine and instead I wanted to do cosine, if I was doing cosine, so COTA, that's the adjacent side when compared to the hypotenuse. So for angle A, that's going to be 15 over 18. Cosine of angle A is 0.8333. If I reverse look up that 0.8333, so inverse cosine of 0.8333, I get 33.6 degrees for angle A. as I should. It shouldn't be different. It should match what it is that you're finding the angle of. It shouldn't be different if you use sine or cosine. That means that I'm going to go through and do the tangent. The tangent is the side opposite when compared to the side adjacent. In this case, 9.550 is opposite angle A, and 15 is adjacent angle A. So the tangent for angle A is a different ratio, 0.6633. But when I reverse look up that tangent, so tangent inverse of 0.6633, I get 33.6 degrees. Again, notice that all three of these are the same. The measure of angle A is going to be the same for all of the ratios. We'll do a second example. This time we're going to find the measure of angle B. All three sides of the triangle are known. We have a side that is 10, a side that is 13, and a hypotenuse of 16.401. For angle B, think about where you're planted now. Where is angle B? The sine would still be the side opposite angle B when compared to the side that is the hypotenuse of the triangle. The side opposite angle B is the green dot, or 13. The hypotenuse is always across from the right angle, so that's going to be 16.401. And the sine of angle B is 13 divided by 16.401. Dividing that out to get the decimal, angle B is 0.7926, and using the inverse to reverse look up, I have sine inverse of 0.7926, which is 52.4 degrees. If I do the same problem using cosine, the cosine for angle B is the side that is adjacent, or the pink, compared to the hypotenuse. That's going to give us 10 divided by 16.401, which is 0.6097. When I invert that, I get that angle B is the cosine inverse of 0.6097, or 52.4. Lastly, the tangent would be the same, except the tangent is the ratio of the opposite side when compared to the adjacent side. Now for angle B, the opposite side is 13, the adjacent side is 10. So angle B would be 1.3 with a few zeros after it. A tangent of angle B, would be 1.3 with a few zeros after it. And angle B would be the reverse tangent, or the inverse tangent, of 1.3, or 52.4. Again, confirming that no matter which of the three ratios you use, you should get the same measurement for the angle. They all go back to the same angle. All right? Okay, let's practice doing various unknown sides and angles within a triangle. Okay, here we go. I have 3 different examples here. In each one of these examples, I have an x value for an unknown side. So in this start, we're going to be finding unknown sides. Okay, we start with what we know. In the very first triangle, AKH, if we look at the angle at H, that is known to be 42 degrees. I want to start with the information I know. Across from the 42 degrees, we have our variable x. We know that 6 is our hypotenuse. We do not have any information on that adjacent side, AH, so we're going to leave that blank. Using only the information we have the angle at 42, the side length that is x, which is opposite that angle, and the measure of the hypotenuse is 6. Of our 3 trig functions, which of them is reliant upon the side opposite the angle and the hypotenuse of a right triangle? that would be your sine. So we're going to start with the sine of sine of 42, which is the angle that we know, is equal to x over 6. Sine of 42 is the side opposite over the hypotenuse. I'm going to rewrite this as a proportion. So I'm going to use sine 42 over 1 has to equal x over 6. I wanted it as a proportion because I do know how to cross multiply. I know that I should be able to take 6 times the sine of 42, and that should equal 1 times x. So now on my calculator, I'm going to type in 6 times sine of 42. And I get 4.105, 4.015. Since 1x is the same as x, this means that our missing side length x has to equal 4.015. Let's try the second example. In this example, I have triangle RNM, and I know the measurement at the angle R. So I'm going to sit from that view. For that measurement of 37 degrees, my x is again opposite that angle. But the side I know this time is adjacent to that angle. Which of our 3 trig functions uses the side that is opposite and the side that is adjacent? For opposite and adjacent, I need the tangent function. So the tangent of 37 degrees has to be the value of x, or the side opposite, when compared to the side adjacent, or 15. Tangent of 37 is x over 15. So again, I'm going to rewrite this as tangent of 37 over 1 is equal to x over 15. This is simply done so that I can have a proportion, and then I can cross multiply. 15 times the tangent of 37 has to equal 1x, or x has to be 11.303. So I'm going to do 15 times tangent 37, and that's going to give me 11.303. And the value of x has been found. In the third example, I put a little pencil up there because this one is one of the trickier examples because the hypotenuse is missing. So I thought I would highlight this example by saying, of all of them, this would be one I would write down. All right. Angle D is known to us. So that is 70 degrees. When we look at that 70-degree angle, we see that 8 is the adjacent side and that the missing side is the hypotenuse. So of the 3 trig functions, which one uses the adjacent side and the hypotenuse? That would be cosine. So toa. Cosine is the adjacent side compared to the hypotenuse. That means that I can use the cosine of 70 degrees, and that has to equal 8 over x. 8 over x. Notice the x is in the denominator. That's why this one is a good one to write down. This gives us the cosine of 70 degrees over 1 is equal to 8 over x. I'm now going to cross multiply, and I have x times the cosine of 70 is equal to 8 times 1, or 8. So now in order to get x alone, I need to divide both sides by that cosine of 70. X is going to equal 8 divided by the cosine of 70. Do not treat this any differently than you normally would in your calculator. You would just do 8 divided by, hit that cosine button, and then 70. Close the parentheses and hit enter. That should give you that x is equal to 23.390. It's worth noting that in all 3 of these examples, your hypotenuse should be the longest side of the right triangle. So if I look at the very first example, I don't want that one. I want this. If I look at the very first example, 6 should be the longest side in this right triangle. So when I solve for x, it needs to be less than that value of 6, and it is. So while it's not a check per se, it does let me know that I didn't do anything drastically wrong. Similarly, in this last example, when I find the x value, it is across from the right angle, so it should be the hypotenuse, and the hypotenuse should be the longest side. So my value of x at 23.390 needs to be bigger than 8 because it has to be the longest side, and it is. Right? Let's look at 3 more problems where we're not finding the side, but we are finding the angle. In the very first triangle, we have triangle THM, and the triangle THM has an alpha or unknown angle at T. So I'm going to zero in from that view, and I'm going to say that at angle T, I have an unknown angle alpha, but I also have 2 side lengths. I have 10, which is an adjacent side to T, and I have 20, which is the hypotenuse. Where's my 20? There we go. So because I have the adjacent and the hypotenuse, you may have already seen it get big. That would be the cosine. So the cosine of my alpha here is going to be the adjacent side over the hypotenuse, or 10 over 20, which means that my alpha has to be, remember we're looking for the angle, so that's going to be our inverse. So I'm going to use inverse cosine of 10 over 20, or inverse cosine of 1/2, which is indeed 60 degrees. That gives me the value of the angle at alpha. Let's take a look at the second triangle where we have an angle B or beta that's there for triangle QRS. So that angle beta has two known sides in it. We have 21, which is opposite that beta, and 24, which is adjacent to it. Of our 3 trig functions, the one trig function that uses opposite and adjacent is our tangent function. So we're going to use tangent of beta has to equal 21 over 24. Since I'm looking for the angle, I'm going to use the inverse or lookup for 21 over 24. And tangent inverse of 21 over 24. Using the calculator to type that in, I get 41.2 degrees. And I now know the measure of the angle beta. In the third triangle, WXY, I have an unknown angle at summa. Where are we going? Go on, summa. Come on. There we go. There's summa. And so once we've highlighted that unknown angle at summa, I recognize that 35 is opposite that angle, and the 48 is across from the right triangle, or the right angle, so it is the hypotenuse. Of the 3 trig functions, the one that uses opposite and hypotenuse is sine. So opposite, we have 35. Hypotenuse is 48. So the sine of the summa is 35 over 48. And summa would be inverse sine of 35 over 48. Or when I type that into my calculator, I should get 46.8 degrees. And I've been able to use sine, cosine, and tangent each to find a missing angle. All right. Yikes. Here we go. Next one. We want to be able to solve the right triangles all together. That is, identifying all side length measurements and all angle measurements for a right triangle. Here's what that looks like. To solve a right triangle, you need to find the measures of all the angles and all the lengths of the sides. To begin this, you'll need to find at least two pieces of information, such as an acute angle and a side length, or the length of any two of the sides. You need to know one, that it's a right triangle, and two, you need additional pieces of information. Either, excuse me, either a side length and an angle, or two sides. Either one will do. The first example I have is an acute angle and a side length. So we're going to find theta, which is an angle measurement, the measurement of P, the hypotenuse, and the measurement of M, the missing side. Like before, we're going to start with an angle we know. This angle is 35 degrees. So I'm going to start there. From the 35-degree angle, we have the side that is opposite it, but we are missing both the adjacent side and the hypotenuse. So I'm going to start with the adjacent side. I know that opposite over adjacent refers to the tangent. So the tangent of that 35-degree angle has to be 15 over some number m. I'm going to solve this for m. I'm going to write tangent 35 over 1 equal to 15 over m because I want to have that proportion to solve. So m times the tangent 35 is equal to 15, dividing both sides by tangent 35. Keep in mind, tangent 35 is like a big long decimal number. I could figure out what that is, but then I need to keep retyping it into my calculator. So I don't want to have to do that. I'm just going to shorthand it as tangent 35. Those 5 markings, TAN 35, are fewer digits than any decimal that I would need to keep. So I'm going to keep it as tangent 35. That means that the value of m would be 15 divided by whatever tangent 35 is. And now that's what I'm going to type into my calculator. 15 divided by tangent 35. And when I do that, I get 21.422. Because this is a side length, we're going to keep at least 3 decimal places. And I now know that the measure of the side length m is 21.422. Good? Okay. Now, I need to find P. And in order to do that, I'm going to look at that angle that is 35, and opposite it is 15, and P is the hypotenuse. Right? It's blue. Yep. So opposite and hypotenuse are functions, are relationships attributed to the function sine. So I'm going to do the sine of 35 is equal to 15 over P, the opposite side over the hypotenuse. Notice that this one comes out a lot like the last one. Sine of 35 over 1 is equal to 15 over P. Cross multiplying them suckers. P times sine of 35 is equal to 15. I'm going to keep sine of 35 together because it's just a big long decimal. And I'm going to get P is equal to 15 divided by that sine of 35, which means that the value for P is going to be 26.152. Notice that P is the hypotenuse. It should be longer than the other two sides. Is the 26.152 longer than the 15 and also longer than 21.4? Yes, it's longer than both 15 and the value of m that we found, which means that at least we haven't totally messed this up, right? Okay, I have another missing value, that of, I forget what that's called, theta? I think that one's theta. Missing value of theta. So now, in order to do that, there's a couple of different things. I could go ahead and use my trigonometry. I got some now. I could do, 15 over, or I could use the m and the 15 or the p and the 15. But this one might actually be a bit easier. We know that the three angles of a triangle have to add up to 180. If the right angle is already 90 degrees, then that angle there at theta should just be 90 minus the 35. We've already got a right angle, which is 90 degrees. So we've used up 90 of the 180. That leaves 90 left. So if I do 90 minus 35, I get 55 degrees, and that should just be the angle at theta. So I knew three pieces of information. I knew the side that was 15, the angle that was 35, and the right angle. And I found the three missing pieces, theta, p, and m. This is what solves the right triangle. We now know all the side lengths and all the angle lengths, right? Okay. If we don't, if we have a different setup, that is, if I only have two side lengths and the right angle. So now in the second example, I'm going to need to find alpha, alpha, phi, and t. So phi is the 0 with the line slash. That's actually phi. So I've got to find phi, alpha, and t. I think I've got my Greek letters wrong. I'm just going to call it phi, alpha, and t. Let's start with phi. If I start with phi, see how I've highlighted that in green? And I look across, I have 16, and adjacent to it, I have 23. 16 and 23. That's opposite and adjacent. Of the three trig functions, tangent uses opposite and adjacent. So from phi, 16 over 23 is the tangent. That means that phi should be the inverse tangent of 16 over 23. Typing that into a calculator, I get that phi is 34.8 degrees. Inverse tangent, second tangent, 16 divided by 23, enter. That should be my first angle. To get the angle at alpha, that is the other angle, I could do 90 minus 34.8. That's absolutely fine. No issues there. I'm not going to, though, because if I messed that up, I won't know it. If I just subtract that from 90, I won't know if I've messed it up. I don't want to compound my errors if I can't, if I don't have to. So from alpha, I know that the 23 and the 16 are known to me. 23 is opposite that alpha, 16 is adjacent to it. So again, I can use tangent, but this time from alpha. And when I do that, I have 23 over 16. That means alpha has to be the inverse tangent of 23 over 16. And alpha is 55.2 degrees. Now, I can check these two because they should add up to 90. So if I add 34.8 to the 55.2, I do get 90 degrees. So I can at least validate that that part checks out. The third piece I have to find is the length of the side that is t. You could do this a couple of different ways. You could use either the sine or the cosine of either one of those angles, phi or alpha, in order to set it up. You could also use something that doesn't involve trigonometry, but we have practiced already, and that is Pythagorean theorem. Because it is the hypotenuse that's missing on a right triangle, we know that a squared plus b squared has to equal c squared. So 23 squared plus 16 squared has to equal t squared. Multiplying or squaring the 16 and squaring the 23 and then adding them together, we get that 785 has to equal t squared. Square root of both, the square root of 785 has to equal the value of t, which means 28.018 has to equal the t value. Now that I've found the three missing pieces, I have solved this particular triangle. I know all six values. That is the value of all three of the angles and the value of all three of the sides. the triangle is considered solved. I have two more examples to follow. In the first example here, I have a theta, alpha, and C. I'm sorry, theta, A, and C. A and C are missing sides. Theta is a missing angle. So to begin, if we start at the angle that is 78 degrees, A is opposite it, 3 is adjacent to it. Opposite and adjacent is tangent. So the tangent of 78 degrees has to equal A over 3. This means when I cross multiply it, 3 times the tangent of 78 has to be A. 3 times tangent of 78 is 14.113. So the value of A is 14.113. Going in to find C, I see that I have the side that is adjacent and the side that is the hypotenuse. I'm going to use the adjacent side because it's number 1 shorter. It's just 3. But 2 because it was given to me. I'm starting with the given information first and giving it preference to use. Because if I did 14.13 through 113 wrong and I use it to find more answers, it's just going to continue to be wrong. So I always want to start with the known information. So for 78 degrees, I need to find the hypotenuse C. I know the 3. 3 is adjacent. C is the hypotenuse. Adjacent and hypotenuse is cosine. So the cosine of 78 degrees is 3 over C. That's the adjacent side compared to the hypotenuse. Writing it out as a proportion, I have cosine of 78 over 1 is equal to 3 over C. Or C times the cosine of 78 is equal to 3. Dividing both sides by cosine of 78, I get C is equal to 3 divided by the cosine of 78. Typing that in, C is 14.429. That gives me the value of the hypotenuse. Now, as a reminder, the hypotenuse should be the longest side. Since C is the hypotenuse, the 14.429 is longer than both the 3 and the 14.113. So that's good. Now, the one thing I do have to find here is the phi value. That's not phi. Did I say phi? I have to find the angle value. So if I look at that angle measurement, it should, with the 78, add up to 90. So 90 minus 78 gives me 12. And the missing angle measurement is indeed 12. All right. Let's take a look at the next one, where again we have two sides and the 90-degree angle. That's all we got. So if I take a look at alpha, we'll start again at alpha. I see that the side that is 5 is adjacent to it. And I see that the 18 is the hypotenuse. That should be blue. That should be blue, not pink. It should be blue. I wonder if I can. I don't think I can. I don't think I can change it at this point. But that 18 should be under a blue circle. So adjacent over hypotenuse is cosine. Cosine of alpha would be 5 over 18. So the alpha should be the inverse cosine of 5 over 18. That means alpha is 73.9 degrees. If I go for the R value, I'm not going for the R value at this point. I'm going for phi. Phi should be the opposite over the hypotenuse. I don't know why it's pink. It should be blue. Opposite over hypotenuse is sine. The sine of phi is going to be 5 over 18. But wait, that's the same. That's okay that it's the same because we're using a different trig function. Cosine and sine are different trig functions. So the sine of phi is still 5 over 18, but this time it's the sine ratio and not the cosine ratio. So phi would be the inverse sine of 5 over 18, and that's going to be 16.1. Now, I've got the two angles. I still need to find R. I've got those in the wrong order. R is not the hypotenuse. R is a side, 5 is a side, 18 is the hypotenuse, but I know 2 of 3 sides of a right triangle. So I can again use Pythagoras' theorem. This means I can use a squared plus b squared equals c squared. In this case, I have 5 squared plus r squared has to equal 18 squared. 5 squared is 25, 18 squared is 324. So r squared is 18 squared minus 5 squared, or 324 minus 25. R would be 299. So r squared would be 299. R will be the square root of 299, which is 17.292. Keeping in mind that the hypotenuse should be the longest side, and our hypotenuse this time out is 18. 18 should be longer than the r value that we get, and 18 is bigger than 17.292. So we have also solved this right triangle. We know the measures of all the angles and the lengths of all the sides. All right. We only have, that's where that went. We only have one piece left, which is our applications. This is just a small sampling of word problems that use trig to solve them. And I am going to try to do these in real time as we write them, and I hope that it works out well. I have 3 problems to go. Here we are. Here we have a sign that is attached to a building. I'm going to get my pen here. What color do we want? Let's do purple. A sign is attached to a building by a triangular brace. If the horizontal length of that brace is 48 inches, the angle at the sign is 60. What is the length of the wall support? So I've got this angle measurement. I've got the 48 inches, which is, well, is it? Okay. And then this is the side I'm trying to find. Oh, that's an interesting way to mark it. All right, so I'm going to start by identifying this as the hypotenuse, right? Because my right angle would be here. So the hypotenuse should be here. If I've got the angle at 60 degrees, then 48 would be the adjacent side because it's right next to it. And X here would be the side opposite. So based on the 60 degrees, I need the side that is opposite. I have the side that is adjacent. Opposite and adjacent means I'm looking for tangent. So we're going to do, oh, why are we having some issues? Let's erase. Let's see if we can get this to work. Only now that I'm presenting, it doesn't want to work. There we go. The tangent of 60 degrees has to equal the side that is opposite, which is X, when compared to the side adjacent, which is 48. I'm going to rewrite this as a proportion. Tangent of 60 over 1 is equal to X over 40. When I cross multiply, I'm going to have 40 times that tangent of 60 degrees. Whoops. Tangent of 60 degrees has to equal my X. Pulling out my calculator, I am literally typing in 40, and then I'm going to do times tangent 60, close my parentheses, and hit enter. And I get, where's my 69.282 inches. is equal to x. So the length of the wall support here, the value of x, is 69.282 inches. And that's it. That's my first application. All right, let's try the next one. Here we have a jet on a runway. At what angle must a jet descend if it's 900 feet above the beginning of the runway, and it must touch down 1,500 feet from the runway's beginning? So the altitude of this jet is 900 feet. I'm going to write it over here. Okay, let me get rid of, let me see if I can get rid of that, erase. Put in, yeah, I know, y'all don't care. You just want me to keep going. That's fine. Yeah, 900, and it must touch down. So we've got 1,500 feet of runway. So we're going to do 1,500 feet of runway at an altitude of 900. And we need to find this. This is called an angle of, declination. So rather than being at an incline, it's at a decline. So this is sometimes called the angle of decline or the angle of declination, meaning from a horizontal going down. So I've got this angle that I'm supposed to find. I know that the height or altitude of the plane is 900 feet. And the amount of runway it has is 1,500 feet. So from beta, I have the side that is opposite and the side that is adjacent. Opposite and adjacent means, again, I'm using the tangent. This time, it's going to look like the tangent. Oh my gosh. It's going to look like the tangent of beta. There we go. Grab this again. Pen. We're going to look like the tangent of beta. See if that's easier. Has got the equal opposite, which is 900 over 15,000. So I need to find beta. I need to undo the tangent. So beta is going to be tangent inverse. And I can figure out what that is, or I can just type into my calculator 900 over 15,000. I think I'm just going to type in the 900 over 15,000. I think that's just easier. Now, because I'm using the inverse tangent, I'm going to hit second, clear my calculator, second, tan, and then 900 divide by 15,000, close my parentheses and hit enter. And I get that beta is going to be 3.4. And since it's an angle measurement, that's got to be in degrees. So it's going to be a 3.4 degree decline, which makes sense. You wouldn't decline by a lot, but rather by a little. So we need a 3.4 degree decline. Like if it was a 30 degree decline, I mean, that knows that plane just plow right into the ground. That ain't happening. All right. One more I've got. This is actually a family story. At the Ark of St. Louis, my brother-in-law really did stand at a wall 120 feet in front of the Ark. I don't know the exact measurement, but he really did stand at a wall in front of the Ark and made it look like the arch at St. Louis was like resting on his head. That's what this first picture is supposed to be. This is my brother-in-law, Bill. That's actually his name, Bill. And he is 6 feet 4 inches tall. Now, my sister stood 10 feet away, assuming at eye level. And the question is, at what degree here did they have to incline or bring up the camera? And then can we use that to estimate the height of the ark? And the answer is, yeah, we can. I'm going to start with what we need. Assuming right triangles here. We're going to assume a right triangle here. We've got a right triangle there. For the angle of incline, that is from the ground up, I know 6 feet 4 inches. 6 feet 4 inches is 6 1/3 feet. And that is opposite the angle. Adjacent the angle, I have 10 feet. So again, we've got opposite and adjacent, which works us into tangent. We do a lot of tangent here. And that has to equal the tangent of this alpha. Which means I need the inverse tangent of 6 1/3, dividing it by 10. That's going to give me my alpha. All right. Calculators out, because you can't figure this out without a calculator. At least not where we are. So I need second tangent. Then I'm going to do 6 1/3. So that's my fraction. Divide that by 10. And when I hit enter, I get 32.3 degrees. Because this is an angle that I'm looking for, I get 32.3 degrees is my alpha. Beautiful. And I've got one. I've got the angle of inclination. Now, how do I find the height of this arc? I need to find h. Well, there's two different ways to do this. We've done similar triangles, so you can do that. You can do h over, we need the whole thing here. That's 120 plus 10. So h over 130 has to equal 6 1/3 over 10, which means 10h has to be 130 times 6 1/3. Boy, you guys understand now why I love to do the 130 times 6 1/3. So I get 10h. I'm getting 823 1/3, which if I divide that by 10 to solve for h, I get h is 82 1/3 feet. Yeah, that's not right. That's a ridiculous amount. Certainly it's not real. Can't be 82 1/3 feet for the St. Louis Arch. It would be much taller than that. But mathematically, that's the value that I'm getting. If you want to use a similar triangles to do that, you certainly can. The other option would be to say that the 32.3 degrees or tangent, let's see, I'm going to change colors here. Let's erase that. 10. Let's do a new color here. If you want to use trig on it, it could be that the tangent of the 32.3 degrees has to equal, so if we're doing tangent, that's got to be opposite, which is h, over the adjacent, which now is going to be the whole side of 130. So 130 times the tangent of 32.3. Tangent 32.3 could equal the h. So let's see what I do. 130 times tangent 32.3, close my parentheses, equal, and I get 82.2 feet. Well, that's pretty close, right? Because in this first example, I get 82 and a third, or 82.33333, and here I get 82.2. So that's close. As close as it would be in horseshoes, right? And we get that. Okay, I found the height of the arc, even though it makes no sense. I did find a value. Height of the arc would be 82.2 feet, and I found the angle of inclination at 32.3 feet, 32.3 degrees. And I've got that guy and that guy. All right, cool. What have I got left? Well, I have a page here for summary. So, what to do when you're calculating a ratio. Make sure you know the opposite, adjacent, and hypotenuse. Make sure that you know the values, which of the trigonometric functions fits the information, the sine, the cosine, or the tangent. And then you want to make sure you're simplifying the ratio to lowest terms or converting it to decimal form, whichever is most appropriate at the moment. If you have to find the angle measurement, again, you want to make sure you know the side opposite, adjacent, and where the hypotenuse is. You want to make sure you've determined which of the trigonometric functions best fits your information, the sine, the cosine, or the tangent. You want to apply the inverse trig function, that is the second and then the appropriate trig function. If you know two of those three angles, you may use subtraction. That is absolutely fine to do. The third thing that we talked about was finding the missing side length. Again, know which side is opposite, adjacent, and hypotenuse. That will help inform you on which of the trig functions you are using, the sine, the cosine, or the tangent. We're going to solve for the side length algebraically using a proportion. Or if you got really lucky, you might be able to use Pythagoras' theorem. If you know two of the three sides, you can choose to use Pythagoras' theorem. Okay? If you have any questions, if you are confused about any of this information, you can follow up with me or please stop into the Math Center for additional assistance. This was a long one. I do have the chapters marked if you need help. Thanks.